Okay, good morning, everyone. Now, I have already shared two videos about 5.1 and 5.2. 5.1 was introduction to the definite integral. At 5.2, it is about Riemann sum and the use of sigma notation. And now we are going to have actually the definition of the definite integral. So what do we have in this section? We have definition of the definite integral, integrable and non-integrable functions, and properties of definite integrals, area under the graph of a non-negative function, average value of a continuous function revisited. So in this section, we consider the limit of general Riemann sums as the norm of the partitions of a closed interval AB approach zero. This limiting process leads us to the definition of the definite integral of a function over a closed interval AB. Anyway, so now we are going to see the definition of the definite integral, and still we are not ready yet to calculate the integrals of functions. Okay, now you'll see that this definite integral is just the limit of our Riemann sum. Okay, and after that we will see some properties. In our next class in 5.4, we are going to prove the fundamental theorem of calculus. Actually, we have part A and part B, and after that we will focus on calculating what is that, improving our techniques. How do we calculate definite integrals? So now the definition of the definite integral is based on the fact that for some functions as a norm of the partitions of AB approach zero, the values of the corresponding Riemann sum approach a limiting value J. Anyway, guys, simply what actually the definition is that you have to understand. Okay, so now we actually are given a function f. The function f. So we are talking about the function f. In 5.1, right, actually we studied how to form our partial sum or how to approximate the value, the area of a region, right, which is bounded by some curves or lines. Now, still we are talking about this in the second, in 5.2, maybe you didn't have time yet to study this one. After studying this, you'll understand this much, much better. In 5.2, actually, we studied how to form a Riemann sum. So we are talking about the Riemann sum. What is Riemann sum? It is the partial sum, right? The partial sum of the Sn. We are just drawing some rectangles that is completely maybe inside that region, right? And after that, we are just summing the areas of these rectangles. And after that, we are just actually watching, right, what's happening here if we increase the number of rectangles. So that means that we are actually watching here the values of this one, right? It must be approaching a number. So that's why if let f of x be a function defined on a closed interval AB, we say that the number j, what is j? It's a limiting value. The number j is the definite integral of f over AB, and that j is the limit of the Riemann sum. And this one is Riemann sum. You should really practice how to form this Riemann sum because, as I told you, in integrals, this Riemann sum is one of the most important concepts. Even I'm going to ask the for sure one question in the final exam, forming Riemann sum and evaluating the area using the limits of this Riemann sum. If the following condition is satisfied. Okay, so what is this condition? This condition is just a definition of the what is not definite integral? It is a limit. So given any number epsilon, positive epsilon, there is a corresponding number delta, positive delta. If you remember, it's just exactly the definition of a limit, right? How did you give the definition of a limit? Limit of f of x as x approaches a is equal to L, right? If given any positive epsilon, there is a corresponding positive delta such that for every partition, so now we are saying that every partition, regardless of how you're going to choose these points over the line segment AB, right? With this, actually, this norm means that even the longest, right, the longest interval is less than delta. And any choice of CK in this subinterval, we have, what is it, this inequality. What is this inequality? As you see here, actually, this one is our Riemann sum. This part is our Riemann sum. I can just label this by, let's say, S sub n. and minus this one is j is less than epsilon. Okay. So what is it? Actually, this definition is equivalent to this. This definition is equivalent to this. So this limit as n approach positive infinity. So our real sum as n is equal to j. Okay, this is exactly the same thing with this. So that means that if this limit exists, okay, then we are saying that actually this function is integrable, or we call this definite integral. Now we are going to say that this special limit then, if this exists, then this j, we are going to define this as what? As definite integral from a to b, and here we have f of x and the dx. Okay, this j, if this limit exists, then that is the definite integral of f of x over ab. So now here, after using this one, okay, this definite integral, so here this a, we call this lower limit of integration because we are starting integrating the function starting from a, right? So this actually extended, right, or stretched as this integral sign. And why? Because sigma notation, that's why they use this s, stretched s. And this b is upper limit of integration. And this is f of x is the function to be integrated, right, or the integrand. So x is a variable of integration. And what is this? And this one is all integral of f from a to b. So when you find the value of the integral, you have evaluated the integral. Okay. And so we have no idea how we are going to evaluate this. What I know here is now we are going to give the definition that if f of x is a positive function over the interval ab, then this integral gives us the area under this curve. Okay. Let's just do the theoretical part. Okay, we're not going to use this much, but at least let's just read it and move on. If a function f is continuous over the interval ab, or if f has at most finitely many jump discontinuous there, then a definite integral exists and f is integrable over ab. Actually, that's what important theorem is saying, that if our function is continuous or partially continuous, that means that we have some discontinuity, but still, it is not infinite. It is finite. Finite means that, okay. Like, for example, the first one, it is completely continuous function. Let's say we are given kind of function here. So this one is, it is a, and this one is, it is b, right? So that is the graph of the function y is equal to f of x. And this is our x-axis and the y-axis, right? And how about the second one is, or if f has at most finitely many jump discontinuities, right? Many jump discontinuities, maybe it is something like this, okay? So jump discontinuities, let's say we are given a function like this, okay? So this one is a, and this one is, let's say it is c. And here we just continue from here, okay? And this another function, this is the same function, okay? Let's say this d, and from here, let's say our function is something like this. So this one is c, right? As you see here, this function at c, at a, at c, it is not actually continuous, right? But still, this function is, what is it, differentiable? Because here, our function is defined differently, and here it is different, here it is different, right? We call such functions piecewise defined functions. Still, I can integrate this. Why? Because soon we are going to see its property, the integral of this function from a to, this should be b, not c. Okay, so here we have f of x dx. I can integrate this from a to c, and here we have f of x dx plus integral from c to d, and again here we have f of x dx, and integral from b, this one is d, to b. And here we have f of x dx, okay? So this is how we're going to integrate this if our function has finitely many jump discontinuities in the interval ab. Anyway, what you have to know here is if you are given a continuous function over the closed interval ab, always we can integrate this. And also, if it has finite jump discontinuities over this interval, still it is integrable. Okay. Properties of definite integrals. Now, again, actually, we are just going to use the definition, or how do they form the Riemann sum. Using the definition, we can prove all of these properties. But again, we are really running out of time. That's why I just want to focus on the main concepts and the main theorems, okay? And during our physical class time, I'm going to solve only problems. So when f and g are integrable over the interval AB, the definite integral satisfies the following groups. So that is order of integration. The integral from a to b f of x dx is equal to minus b to a f of x dx. Why? If you just take only one actually line segment, right? So for example, let's say here we have x sub k minus 1, and this one is x sub k. So when we are forming our delta x, right, what is our delta x? Delta x is equal to x sub k minus 1 minus okay. So here, this delta x is equal to x sub k minus x sub k minus 1, right? So now, how about if you integrate the starting from b, right, to a, now in the reverse direction? At the time, what will be your delta x? Now, instead of delta x, we will have minus x. Why? Because if you take this one, right here, we have x sub k minus 1 minus x sub k. It gives us minus delta x, right? And that's why just we have minus, and we can interchange the integration limits. And zero width interval. How about if you integrate the function over a single point from a to a, means a single point, right? A single point that's equal to 0. Why? Because its width is 0. And how about constant multiple? If you multiply the function by k, right? Again, here we have sigma notation, right? Using that property, if we have c, I can take out this k out of this integral. If you remember, because this integral means that it is limit of the sigma notation here, right? The sum. So we are just using this property. And here we have, let's say, c times a sub k, right? So I can write it as c times sigma, and here we have a sub k. Because again, you should understand that this definite integral, right, from a to b, k times f of x dx, it is the limit of this partial sum, or limit of this Riemann sum. And sum and difference from a to b, f of x plus or minus g of x dx is equal to integral from a to b f of x dx plus or minus integral from a to b g of x dx. Again, we are just using the properties of the sigma notation and also the properties of the limit, right? We know that limits of f plus g is equal to limit of f plus limit of g, or that's equal to L plus M. And additivity, again, I have just shown this here, right, in the previous slide. Especially if the function has some discontinuity, jump discontinuity over this interval, again, we can just split this into smaller regions or different regions. So integrating from a to c, the f of x dx is the same as integrating from a to b and b to c. Okay. And maximum minimum inequality. If f has minimum value, a maximum value, max f, and minimum value, minimum f on AB. And also, if you remember, we had a theorem, right? If our function is continuous function over the closed interval, then it must have global maximum and it must have global minimum. So those global maximum and global minimum, we are just denoting by max f and minimum f, because for the function to be integrable, it must be continuous, right, over the interval. So now then we have this, what is this? We have this inequality. Minimum value of f times b minus a is less than or equal to integral from a to b, f of x dx. It is less than or equal to maximum value of b minus a. Okay, So why is this so? Because as you see here, we can just draw one actually graph, and just to visualize this, you can see that suppose that our function is something like this. Okay, so this one is A, and this one is B. All right, and this inequality is saying that the area under this curve, right? The area under this curve, let's say we're talking about this one, is always between these two rectangles. What is it? The first one is, it is minimum value of f times b minus a. What is it? It is this rectangle, right? It is this rectangle. So actually this rectangle. And how about, because this one is the minimum value of f. Let me just label this. It is minimum value of f. And how about this maximum value of f times b minus a? We are talking about this rectangle. Talking about this rectangle. So this one is, this value is maximum value of f. So as you see here, the area under this curve is always between these two rectangles. It is greater than this thinner rectangle and less than or equal to this big rectangle. Because at the same time as f of x, it may be a constant function, right? And that's why also we have equal sign here. And domination, like limits, if f of x is greater than or equal to g of x on closed interval ab, then the integral of f of x from a to b is also greater than or equal to the integral of g of x from a to b. And our f of x is, if our f of x is non-negative function on the closed interval ab, then also it is definite integral is always non-negative. It must be non-negative. Okay, these are the most important properties of definite integral. Now, once again, we are just step by step, we are learning how to stand, now how to walk, and still we don't actually know how to walk properly. That means that we don't know how to solve actually integrals. And now just using the definition or using the properties, how we are going to solve, or we can solve this problem. It says in this question, suppose that the definite integral of f, some kind of function, we don't know what kind of function is it, from -1 to 1 is equal to 7. And definite integral of 1 to 5, f of x dx is equal to -3. And -1 to 1 of g of x dx is equal to 11. Evaluate the following, okay, using the properties. Now from 5 to 1, but I know that 1 is 1 to 5, right? By using the first property, I can rewrite this as negative minus integral from 1 to 5 and f of x dx, right? And this integral is given, that's equal to -3. So it is minus 3, and that's why this integral is equal to 3. And how about this one from -1 to 1, right? 3 times f of x minus g, 5 times g of x. Again, using the properties of the integral, I can rewrite this as 3 times integral from -1 to 1. And here we have f of x dx minus 5 times integral from -1 to 1, g of x and the dx. That's equal to the first part, this -1 to 1 f of x dx, that's equal to 7, right? So here we have 3 times 7 minus 5 times, how about g of x? G of x is equal to, it is 11. So this answer is equal to 21 minus 55, that's equal to 34 minus. And the last one from -1 to 5, right? And see here, we don't have such integral, but from -1 to 5, I can rewrite this integral using property for everything. I can write it as from -1 to 1, right? F of x dx plus integral from 1 to 5. It is f of x and the dx. Now the integral from -1 to 1 f of x dx, that's equal to 7. Plus integral of f from 1 to 5, right, of the f of x dx, that's equal to -3. So the answer is 4. Show that the value of this definite integral from 0 to 2 under the root actual square root of 1 plus sine of x dx is less than or equal to 2 times square root of 2. Okay. So now we are going to use the inequality property, right? And once again, we know that what is that? Actually, a definite integral, right? Is always between these two functions. Minimum value of f times b minus a is less than or equal to definite integral from a to b, right? Here we have f of x dx, and that's less than or equal to maximum value of f times b minus a. Now, if you use this property, okay, so then the value of this definite integral is always between minimum value of f times b minus a. What is b minus a? It is 2 minus 0 less than or equal to integral from 0 to 2 square root of 1 plus sine of x. And dx less than or equal to, so here we have maximum value of f times 2 minus 0, right? So now what is the minimum value of f? Let me first evaluate this and substitute here. What is the minimum value of f? That is 1 plus minimum value of sine of x is equal to negative 1, right? So that's equal to 0. And how about maximum value of f? The maximum value of f, maximum value of sine of x, that's equal to 1. So that's equal to square root of 2. Now, if we substitute these values into this inequality, then we get this inequality. Minimum value of f, that is 0. 0 times 2, it is 0. Less than or equal to integral from 0 to 2 and square root of 1 plus sine of x. And dx, that is less than or equal to maximum value of f, that's equal to square root of 2. And here we have 2, that is 2 times square root of 2. So that means that actually the value of this definite integral do not or cannot exceed the value of 2 times square root of 2, right? So now we have just proved that this, as see here from this inequality, is always positive, and at the same time is less than or equal to 2 times square root of 2. Area under the graph of a non-negative function. So since actually how we are evaluating or what we understand from this definite integral, right? If you're given any function, first we have to draw this curve, right? Or the graph. And after that, we are actually forming some kind of rectangles, right? In a ordered manner. And after we are just summing up the areas of this rectangle. So if y is equal to f of x is non-negative and integrable over a closed interval ab, then the area under the curve y is equal to f of x over ab is the integral of f from a to b. Okay, so it is the area under the curve. It doesn't mean that it means the area, it means one interpretation of this definite integral. Okay, if you're given a non-negative function, that means that this graph is totally over or above the x-axis, then the area under the curve over this AB is just the integral. So that means that to find the area, just use the integral. But we are not saying that this integral is the area. Okay, you should understand this statement well, because we are just talking about here one application and one use of this definite integral. So now if you want to find the area under the curve, just we have to evaluate this definite integral from a to b. Okay, so since it is non-negative, right, usually what kind of function is it? Its graph is totally above the x-axis. Maybe our function is something like this. Okay, this one is a, and this one is b. All right, so we are talking about this area under this curve. How do we find this? Okay, this irregular shape. So as you see here, without the help of integral, it is not easy to find the area under this curve. So now this actually definition is saying that if you want to find the area, just evaluate this definite integral. If I know this function, actually, if y is equal to f of x. If you evaluate this definite integral, the answer, right, the result of this definite integral, it can be interpreted as the area of the region under this curve, and which is bounded by the vertical lines x equals a and x equals b. Example, compute this definite integral from 0 to b dx dx and find the area under area a under y equals x. over the interval from 0 to b. And the second one is from a to b. Third one is and the a to b, but here our function is c. A to b, it is x squared. Okay. All right, let's go one by one. Let me go right into parse here. Solution. Okay. Let's have the first one. Computes from 0 to b x dx, right? So let's write here. It is a. The first one is something like this. And this one is x-axis, a y-axis. And from 0 to bx, it is, we are talking about this function, right? So this one is, it is b. And also this point is b, right? It is b. And we are talking about this area. It's asking here. And since actually compute this one, so this integral from 0 to b x dx over this AB, right, from 0 to b over this interval, the functional negative, that means that this definite integral is just equal to the area under this curve. Now, what is the area? That's equal to 1 over 2 times base, it is b, times b height, right? It's just simply is equal to b squared over 2. Still, I don't know how to calculate this, but from the definition, you know, without calculating, we can actually write the answer of this definite integral. And how about b? How about if it is from a to b, not from 0 to b, from a to b? So a to b is, let's say this b, we are considering this case. Y, and this one is x. So that's our y equals x. Okay. So this is A and this is B. So we are talking about this region, right? So again, let me just label this by S. Okay, what is S? So this S is equal to, by definition, right? What is it? It is just integral from A to B. Let me just write the integral from A to B and x and dx. By using this property, I can write it as, what is it? Integral from 0 to b, right? F of x is just x and dx minus integral from 0 to a. Because from integral, right, 0 to a plus a to b is equal to integral from 0 to b. We have just actually studied this in our properties. Now, if you evaluate this, the first part from 0 to b, we have just found this. That's equal to b squared over 2 minus, and how about integral from 0 to a, right? It's just instead of b, now we have a. Also, that's equal to a squared over 2. So this definite integral is equal to b squared minus a squared over 2. Okay. In a similar way, actually, we can evaluate this integral from a to b c dx, right? So at the time, this will be what? So this will be, it is b squared minus a squared, right? Actually, in C, it is just a rectangle, right? It's a constant function, y and x. In C is, we're talking about this kind of rectangle, right? So this one is A and this one is B. So this area. And how about is width? It is C. So in C, definite integral from A to B, it is C dx. By the definition, since C is non-negative here, right there, what is this definite integral? It's just equal to the area of this rectangle. That's equal to C times B minus A. Okay. And how about this x squared dx, right? From a to b, x squared dx. At the time, actually, we have to use, what is it? The definition of this definite integral. I had to form the Riemann sum and to evaluate this value. Okay, I have already shown one example. Maybe I can show you some, what is it? Steps, but I don't want to show everything here. Okay. How about part D? In part D is saying that in part D, right? Integral from A to B, x squared dx. So integral from A to B, and here we have x squared and dx, right? Integral from A to B, x squared dx. Now, what is this? If you draw this graph, right, we know that it's just a parabola. So we're talking about this parabola. Okay, parabola. So this one is B, and this is A, right? We are talking about this region. Again, you will see that after actually we prove the fundamental theorem of calculus, it becomes really, really easy. Right now, we don't know how to prove this. So that's why we have to just use the basic definition. Okay. All right. Now, previous ones, using our intuition, we just calculated this. Maybe also using the definition, we can do that. But here, I'm just going to use the definition because I have no choice, right? With this x squared, how can I find this value? So to do this one, now we have to form our Riemann sum. And how did they do that? Again, if I just zoom in, we are talking about this line segment, right? So this one is A, and this one is B. Okay, so now let me just divide this into n equal, what is it, line segments. So now we are just actually choosing some points, right? The first one, and the second one, and the third one, and the fourth one, and the fifth one, blah, blah, blah. Okay, so what is the length of that each, what is it, delta x? Let me just label this by delta x. Suppose the delta x is equal to b minus a over n. Okay, because we have divided this line segment into n equal subintervals. Okay, so now from here, if I just actually choose this x sub 0, x1, how did it form this? Let's see here, x sub 0 is equal to a, right? And how about x1? We have only one jump, so that's equal to a plus b minus a over n. But here we have one. And how about x2? X is equal to a plus 2 times b minus a over n. And dot, dot, how about in general, x sub k? X sub k is equal to a plus k times b minus a over n, right? And the second thing you have to know here is, how about the value of f? Okay, that is f of x sub k, okay? So now we need to find our Riemann sum. At the time, actually just one of them, right? This Riemann sum, let me just write here this Sn is equal to our Riemann sum, it is sigma, and k is equal to 1 to n, right? And what do we have here? Here we have f of ck times delta xk. That's our Riemann sum, right? So now sigma k equals 1 to n. What is f of ck, right? F of ck is here, f of xk. I can just choose this xk. It doesn't matter. I can choose any point from the subinterval from x sub k minus 1 to x sub k. If I just take this one, so here I have f of x sub k and times delta xk, right? And delta xk, delta xk. And let me just write the value of this thing. What is this? What is this? F of x sub k, f of x sub k times delta xk. So that's equal to f of xk, right? So that's equal to our function is x sub k squared, and delta xk, right? So what is x sub k? X sub k is equal to, here we have a plus k times b minus a over n squared, right? And squared times, and how about delta xk? Delta xk is equal to b minus a over n. Okay, so now we have to simplify this one. First, if you actually expand this, here I have a squared and plus, and here we have 2 times a times k times b minus a over n. It's just a plus b squared, right? And the plus, and here we have k squared times b minus a over n squared. Okay, and times, and here we have b minus a over n. Okay, so as you see here, it's quite long, but what we have to do is we have to evaluate this limit, right? So now if you just expand this, what do we have here? Here we have a squared times b minus a over a here n plus, and now here we have 2ak times b minus a squared over n times n, that is n squared, plus, and the last one is k squared times b minus a, and here we have squared as squared, that is cube, cube over, and here we have n squared times n, and here we have n cube. Okay, so now we have to evaluate this limit. So what is this definite integral? This definite integral, right, is equal to limit as n goes to positive infinity, and here we have Sn. Okay, so we have to evaluate this one. Let's see here, this k, okay, this k, I know how to evaluate this. The rest of this one is constant with respect to k, right? Let's see here, the first one, actually, what is it? When n goes to infinity, let me just evaluate this one. So this part, right, when n goes to infinity, that's equal to 0 plus. And how about this limit, right? So this limit is equal to, actually, what is it? I have to evaluate the limit of this one is 2a times b minus a squared over, and here we have n squared, and here we have k, right? What is k? It is n times n plus 1 over 2. We have to evaluate this expression's limit. Plus, and how about this thing? This thing is equal to b minus a squared or cube over, and here we have n cubed. And how about this k squared? If you remember, we have also had a formula to evaluate this, right? So that's equal to k times k plus 1 times 2n plus 1. So unfortunately, I don't have enough space here. Okay. Let me just write it like this. Okay. So that is b minus a cubed. And how about this k squared? That's equal to n plus 1, and 2n plus 1. In the denominator, if you remember, we have 6, and here we have n cubed, right? So now if you evaluate this limit, we will get the answer. Okay, so what do we get here? We get here, the first one is equal to 0. Okay, the first one is equal to 0. The second one, this n cancel each other. That's equal to 1. So here we have a times b minus a squared. And plus, how about this thing? N cancel each other. That's equal to 1. And this one is equal to 2. It is 3. So here we have b minus a. It is cube over. And here we have 3. And now if you just simplify this, we will get this answer. Okay. All right. Let's continue. The average value of a continuous function revisited. Now, average value, we had just seen actually in the first part. I didn't actually spend too much time on this. After all, we are going to use this definite integral. If f is integrable on AB, then its average value on AB is also called its mean, right? Is defined as, what is it? Average value of f is equal to 1 over b minus a times integral from a to b f of x dx, right? And the reason why is it so? Because if you are given a few numbers, for example, what is the average value of, let's say, quiz 1? You just add all the numbers and divide by the number of students, right? But how about our function? We have infinitely many points over the interval from A to B, right? And that's why we are just going to choose n points over this interval. And after that, we are just adding them, okay? And after that, we just find the limit of this function. So see here now, over this interval, right, from A to B. Now, if we choose, let's say, n points, what happens here? Here we need to form our Riemann sum. And after that, evaluate this, okay? And we will get this integral. What do you say this is integral here? This integral, right? That integral is, we have something like this. So roughly, the average value of this function over this interval is equal to, I'm just going to choose a few values here. So we are just adding this f of x1 plus f of x2 plus dot dot. And here we have f of xn, right? And we have n points. And so that is divided by, it is m. Okay. So now, again, if they are equal space, right? We know that actually this delta x would be equal to b minus a over n. Okay, so see here, this we have only n, right? And that's why if I just, instead of this delta x, right? I can write here, what is it? Okay, so for this delta x, we can write, what is it? B minus a over a. Look, how you should understand this average value of f. Okay, let me just write approximately. That is 1 over b minus a times, what is this integral? This integral is, because this sum, right? Sum, we are just adding the values of this f. So that is f of x1 plus f of x2 plus dot dot. And here we have f of xn, and that is divided by m, right? And times, here we have delta x. This dx means it's delta x. The delta x is equal to what? That's equal to b minus a over n, right? Okay. So now actually not to have this b minus a, that's why we need to divide this by b minus a. No. This integral means it's just the sum of the values of this function. And delta x, b minus a over n. So b minus a, okay, they cancel each other. So we have this expression approximately. But when n goes to infinity, it gives us the exact average value of the function f. Yeah. Okay, that's the last slide, and after we'll have break. Find the average value of f of x equals square root of 4 minus x squared. So again, by just using the previous definition here, the average value of f is equal to what? That's equal to integral, and of course, b minus a times integral from a to b, f of x, and the dx, right? So that's equal to, we are actually considering this function over the interval from -2 to 2. So that is 1 over 2 minus 2. And here we have integral from -2 to 2, and the 4 minus x squared and dx, right? And we actually still, we don't know how to evaluate this integral, but we know how to interpret this, right? We know that this definite integral, since our function is non-negative over the interval, right? It's just the area. So what is the area of this semicircle? And here we have 1 over 4 times the area of the semicircle is half times pi times r squared, right? And what is its radius? Radius is 2. It is 2 squared, because this definite integral can be interpreted as the area under this curve. So that's equal to, that is 4 cancel each other. So that is pi over 2. So that means that, again, if you're talking about a piece of material, right? So that area will be equal to the area of this rectangle, whose height is pi over 2 and length is 4. Let's have some break. Okay, we have 10-minute break. After that, we'll continue and talk about important theorems. 10-minute break. I will continue at 11:10.